Hello my dear friends, in this video I'll give you the formula list and I'll solve the problems on beams. We have derived in a video number 2 stiffness matrix for a beam element K is equals to EI divided by LE cube. This equation, how to remember this equation? Check out, you have to remember this 12 4L square, 12 4L square, right? Diagonal 12 4L square, 12 4L square. Upper to this diagonal is remains same 6LE minus 6LE minus 6LE minus 6LE minus 6LE minus 12 2L square 2L square 6L 6L. If you will remember like this, you can easily remember, there is no confusion. Diagonal 12 4L square 12 4L square 12 4L square 12 4L square 6L minus 6L minus 6L minus 12 2L square 6L. See here 6L we have 6L minus 6L we have minus 6L minus 6L minus 6L 2L square 6L 6L 12 12. Symmetric, we have this parameter is symmetrical. Displacement vector, as we have, instead of taking q1 q2 q3, we have a displacement vector v1 theta 1. This is at node number 1, this one is at node number 2. If we have a node number 3, v3 theta 3, clear, and so on. Force vector, for a point load we have f1 f2 f3 f4. For example, two nodes we have f1 f2 for a v1 theta 1, f3 and f4 for v2 theta 2. Maybe f2 as a moment m and f4 as a m. Just generally we have taken f1 f2 f3 and f4. Then we have a next load vector for a uniform distributed load. F is equals to P naught LE by 2. You carefully take down P naught LE by 2 into 1 LE by 6 plus 1 minus of LE by 6 for a single element, for a v1 theta 1 v2 theta 2. Clear. Similarly, we have here for a uniformly varying load, increasing the load from right towards the left direction. The equation is P naught LE by 60. See here 2 we have, here 60. 9 6 LE 21 minus 3 LE. Similarly, increasing the load from left towards the right, then this will remain same P naught by LE. This bottom side value becomes upper side becomes bottom side. So 21 3 LE 9 minus 2 LE. Last value always it is minus. This will not a minus. This will not a minus. Only the last value will get minus. Now sometime he will ask in your problem to find the maximum deflection or at midpoint. Maximum deflection for a simply supported beam, where it will be occurs at the midpoint. This is the maximum displacement which is occurring in a beam. So where the zeta is equals to 0, where the zeta is equals to 0 at the midpoint. When we will consider the zeta is equals to 0, what will happen to the equations? We have derived the Hermite shape function for the given problem. V is equals to h into q. H into q means, we have h means h1 LE by 2 h2 h3 LE by 2 h4. We have found this into q. Q means v1 theta 1 v2 theta 2, this q, right? We have that concept. Now what I do, h1 is nothing but a 1 by 4 into 2 minus 3 zeta plus zeta cube. This is the equation. Just now we have substituted here. Similarly, h2 means we have 1 minus zeta square plus zeta cube divided by 4. h3 means this one. h4 means is this one. Now we need to find out where the displacement at midpoint. Midpoint zeta is equals to 0. Left hand side at node number 1 minus 1, at node number 2 plus 1. So maximum displacement in a simply supported beam at the midpoint, we have this equation. Substitute the value of zeta is 0. This will be goes 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 0. Rearrange this. This value becomes 2 by 4 and this value becomes LE by 2 into 1 by 4. You can see here red color I have marked 1 by 4. Then this will be 2 by 4. Then this will be minus 1 by 4. We have taken 2 by 4 becomes 0.5. 1 by 4 becomes 0.125 LE. and then this will becomes again the value. Just I have rearranged this one, and then this h value I'll substitute again in this equation. We'll have that equation becomes v is equals to 0.5 0.125 1 by 8 into LE, 0.5 this one minus 0.125 LE, V1 theta 1 V2 theta 2. Directly we will use this equation in your external examination, or we'll solve the problem. If they'll ask find the maximum displacement at midpoint, already we have derived, remember this, that's all, we'll get the idea. If you have any confusion, directly use this all the steps step by step, you will get the answer correctly. If you fails to understand, if you fails to remember this equation in your external examination, remember this concept, you will get this answer. Directly use this answer, substitute the value of v1 theta 1 v2 theta 2, you will get a maximum displacement in a element. These are the equations, 4 equations we have to remember. Just these 4 equations, but in we have more than that one. This you have to remember: point load, distributed load, varying load. After getting the complete idea of a beam element, now we'll solve the problem. Problem number 1. Read out: for the beam shown in figure Q1, this is the figure 1 shown in figure, a distributed load, 2 loads we have, determine the end reaction and deflection at mid span. Just now I have discussed mid span, that equation you remember it, that we need to find out. First we need to find out v1 theta 1 v2 theta 2, then that value we need to substitute in that equation. We'll get the value of the maximum deflection at each element at midpoint. Take Young's modulus E is equals to 200 gigapascal and I is equals to 4 into 10 to the power of 6 mm power 4. Here is given in a problem, the beam has a 2 characteristics of the load from fixed end towards the first roller support 12 kilonewton per meter, and from first roller support to the next roller support last end of the beam 24 kilonewton per meter. Double of this load has been applied here. Then first he has taken from fixed end to the first roller support 4 meter, and from first roller support to the last roller support 4 meters he has taken. Based on the applied load and the boundary condition, we are selecting the numbers of elements. Based on this load, we have 2 types of load, the boundary conditions we have here. So with respect to that, I'll take element number 1 is this one, and then element number 2 is this one. Element number 1 and element number 2, 2 elements I'll take. I'll say node number 1, node number 2 and node number 3. So this I'll say as a node number 1, node number 2 and node number 3. This is element number 1 and this is element number 2. How we have to take, just now we got the idea. After getting this idea, we need to take the data here. Young's modulus is given 200 gigapascal. That convert in terms of a meter, we have this units in terms of a meter. All the values I'll convert in terms of a meter. 2 into 10 to the power of 5 Newton per millimeter square we have taken. 2 into 10 to the power of 11 Newton per meter square. All units should be in terms of a meters. Then he has given a moment of inertia 4 into 10 to the power of 5 millimeter power 4. Then that convert in terms of a meters means 1 meter is equals to 1000 millimeter. That means we have 1 millimeter is equals to 10 to the power of minus 3 meters. Millimeter power 4 means into 4, this is power 4. We have 10 to the power of minus 12 multiplied to this value, will get a millimeter power 4 in terms of a meters power 4. That indicates here 4 into 10 to the power of 6 into 10 to the power of minus 12, that becomes 10 to the power of 6, 4 into 10 to the power of minus 6 meter power 4 moment of inertia. Length of the element number 1 L1 is equals to L2 4 meters. For element number 1, load has been applied. Element number 1 12 kilonewton vertically downwards minus 12 kilonewton meter. When you will convert that kilonewton in terms of a newton, minus 12 into 10 to the power of 3 Newton meter. Similarly, here for at node number 2, P naught is equals to minus 24 vertically downwards direction, uniformly distributed load, minus 24 kilonewton per meter, minus 24 into 10 to the power of 3 Newton per meter. We have to find here, we need to find out the ends reaction and Deflection at midpoint. Deflection at mid-span at zeta is equals to 0, V maximum is equals to question mark. Reaction force at end support R is equals to 0. We need to find. The FE model, just now I have told, the given problem is represent in terms of a FE model. As usually the first step of FE model, we have a load variation with respect to first type of load, and this roller support will take as a element number 1, and with respect to this we'll take another element number 2. So we have here element number 1, it is node number 1, node number 2, and node number 3. Node number 1 has a vertical displacement v1 at node number 1, theta 1 at node number 2 due to moment m1 or f2, f1 with respect to v1, f3 with respect to v2, f4 with respect to theta 2 or m2, the moment we have. At element number 2 we have a node number 3. In the node number 3 we have vertical displacement v3 due to the application of force f5, and moment m3 with respect to this force f6, theta 3 will take place. We have a displacement function v1 theta 1, v2 theta 2, v3 theta 3. The length of the element number 1, which is equals to L1, length of the element number 2 L2. This is a FE model. First we need to find out the elemental stiffness matrix for this element number 1, and then element number 2 global stiffness matrix. Then we'll find out the global displacement vector, global force vector, equilibrium equation as usually. Elemental stiffness matrix, as I have told, 12 4L square, 12 4L square, 6 minus 6L minus 6L, 12 2L E square 6L. Here we have a asymmetrical lower diagonal and upper diagonal value. Only a single beam we have, just load variation is there. Same cross-sectional beam element, load variation is there. L1 is equals to L2 is equals to 4 meter. E1 E2 is equals to 2 into 10 power of 11 Newton per meter square. I1 I2 same 4 into 10 power of minus 6 meter square. Then K1 is equals to K2 stiffness matrix, right? So I'll find out for first Ke is equals to that E K1 due to element number 1 we have considered E is equals to 1, E1 I1 L1 cube is a matrix we have. Substitute that value. We have L1 is equals to 4 meters. Young's modulus E is equals to 2 into 10 power of 11. I is equals to 4 into 10 power of minus 6. This is the L1 what we have. 12 remains same. 6 L1 for 6 into 4 minus 12 remains same. 6 L1 6 into 4. Substitute all the value of L1 I1 E1 here. We'll have this equation. Then after substituting calculate this value. That value is equals to 12.5 into 10 power of 3. And we have this 12 is equals to 12, then we have a 24 minus 12 24, and then we have this value is equals to 64, then this value is equals to 32. Similarly you can check out this diagonal values 12 64 12 64. This is 24 24 minus 24 minus 24. We have here minus 24 minus 24, 32 we have 32, minus 12 minus 12, 24 24. Per diagonal and lower diagonal value will remain same. This is the elemental stiffness matrix for element number 1. The first row first column name value we have a node number 1 V1 theta 1, node number 2 we have theta 2 V2. With respect to this V1 we have a first row first column with respect to theta 1, second row second column with respect to V2, third row third column with respect to theta 2, fourth row fourth column. We know that the namings. Similarly K1 is equals to K2, same equation I have copied here. K1 is equals to K2. Why we have here L1 is equals to L2, E1 is equals to E2, I1 is equals to I2. Only we have that characteristics. K1 is equals to K2. We have a node element will get start from node number 2 to 3. Here V2 theta 2 at node number 2, at node number 3 V3 theta 3. With respect to V2 first row first column name, with respect to theta 2 second row second column name, with respect to V3 third row third column name, with respect to theta 3 fourth row fourth column name. Add this K1 and K2 will get a global stiffness matrix. We have only 2 elements. Add that one get a global stiffness matrix. Global stiffness matrix K is equals to K1 plus K2. This matrices we have copied from a step number 2. We have given these names here. These names we have given here. We need to get a global stiffness matrix here. As per the previous method, we'll go with the V1. Here give it that we how many nodes we have? 3 nodes and 2 degrees of freedom. That means 3 into 2, that is equals to 6. We'll have a 6 cross 6 matrix. That means we have a 6 cross 6 matrix. I have taken first row first column name V1, second column and second row name theta 1, third row third column name V2, fourth row fourth column name theta 2, fifth row fifth column name V3, sixth row sixth column name theta 3. Likewise, we need to give where the V1 is there at node number 1, first row first column name V1. Where the V1 is there, here V1. Choose the V1 value. We don't have any V1 value. First row first column name 12 with respect to V1, with respect to theta 1 24, with respect to V1 V2 we have minus 12, V1 theta 2 24, V1 V3 we don't have here 0, V1 theta 3 we don't have here 0. Similarly, we go with the theta 1. So search it here, theta 1 with respect to row. We don't have any theta 1 here. So theta 1 value we'll take with respect to V1 24, 64 with respect to theta 1 with respect to theta 1 V2 here minus 24 with respect to theta 1 theta 2 32 with respect to theta 1 V3 there is no value, so V3 0, theta 3 we don't have the values with respect to 0. Similarly, we'll get a V2 theta 2 value, V3 theta 3 value and V4 V5 V6 whatever it may be we have. We know that how to add that. After adding that, we'll get this global stiffness matrix. Global displacement vector I have shown V1 theta 1 at node number 1, V2 theta 2 at node number 2, V3 theta 3 at node number 3. Similarly, we have a distributed load. We need to find out global nodal load vector. So load vector, if we need to find out, first we need to find out force due 12 kilonewton meter, force due to 24 kilonewton meter. We have a P naught value, but we don't have that forces which is exerting at node number 1 with respect to V1, with respect to theta 1, with respect to theta 2, V2. So I will consider a element number 1, the elemental load vector, that is Fe is equals to P naught Le by 2. Recall that formula list 1 Le by 6, 1 minus Le by 6 with respect to V1, theta 1, V2, theta 2 for element number 1. So we have for element number 1 12 kilonewton per meter, 12 into 10 to the power of 3 Newton meter, L1 is equals to 4. Substitute that values in this equation. We have here this minus 24 into 10 to the power of 3. Why? The direction of force which is applied downward direction, P naught value is equals to what? Minus 12 we have substitute here. We have this value minus 24 into 10 to the power of 3. We have this 1 L means 4, we have 4 by 6 becomes 2 by 3, and then 1 as it is copied minus 4 by 6 becomes minus 2 by 3. So this value we have calculated, that is equals to minus 24 into 10 to the power of 3. Then this value substitute inside, will get some answer that 24 I have multiplied inside 10 to the power of 3 I have taken common, minus 24 into 2 by 3 minus 24 into minus 2 by 3. So we have here value minus 24 minus 16 minus 24 16 value. 24 into 2 by 3 becomes minus 16 into 10 to the power of 3. This value is depends upon V1, this value is depends upon theta 1, this value is depends upon V2, this value is depends upon theta 2. Similarly, consider element number 2. We have a P naught minus 24 into 10 to the power of 3 Newton per meter and L is equals to 4. We have a P naught is equals to minus 24 into 10 to the power of 3 into 4 divided by 2 as it is. This will remains 1 4 by 6, 1 minus 4 by 6. Then this value is equals to minus 48 into 10 to the power of 3. 1 4 by 6 becomes 2 by 3, 1 minus 4 by 6 becomes minus 2 by 3. We have here 48, you multiply inside the vector, we have 10 to the power of 3 common, minus 48 into 2 by 3 minus 48 into minus 2 by 3. They calculate the value. 48 is remain same of this value, minus 32, 48. This is a 32. You take down this as a 48. It is not minus 4. Then these are the values. So this one is v2 theta 2, v3 theta 3. Why? Element will get start from node number 2 and ends at node number 3. The displacement v2 at node number 2 theta 2. Then this one v3 theta 3. We have this concept. Now we'll add these two vectors. We'll get a global force vector for a given problem. F is equals to f1 plus f2 and 10 to the power of 3 into this one, minus 24 16 minus 24 plus 16, 24 minus 16 minus 24 16. We have similarly here minus 48 minus 32 minus 48 32 into 10 to the power of plus 3. 10 to the power of 3 I have taken common here. I'll take here v1 as a 24. We don't have here any v1. Theta 1 becomes minus 16 as it is. We have taken v2 is very much important. v2 we have here and we have here minus 24 minus 48, that is equals to minus 72. Similarly theta 2 we have 16 minus 32, which is equals to minus 16. And then we don't have any theta v3 and theta 3, minus 48 plus 32. All the values you substitute here will get a global force vector. We got a displacement vector, global force vector, and elemental stiffness matrix. After getting all these three values of a given beam problem, bring it in terms of a equilibrium condition, 4-step equilibrium condition, kq into f. K is a stiffness matrix, q is in a global displacement vector, f is in a force vector. We have all these values, substitute all those values. A global stiffness matrix for a beam element is this one, global displacement vector, and then global force vector. We have under equilibrium equation is this one, 10 to the power of 3, 10 to the power of 3 will get cancelled. We have some value here, 12.5 as similar to that we have copied, and then we'll apply the boundary condition for a given problem. Now we'll check out here, we'll compare FE model and this one. Consider a node number 1. At node number 1 all degrees of freedom is equals to 0. v1 is equals to theta 1 is equals to 0. Then we have roller support at node number 2 along vertical direction. v2 is equals to 0, but theta 2 is not equals to 0. Theta 2 is equals to question mark. And then similarly at node number 3 we have v3 is equals to 0. Why? The roller support is given upward direction, vertical displacement is equals to 0, and theta 3 is not equals to 0. Theta 3 is equals to question mark, which we need to find out, right? At node number 3 only two values we need to find out, theta 2 and theta 3. Rest of the values are 0. After that, getting the idea, applying the boundary condition for a given problem and eliminating the rows and columns, we have this concept. Now I'll read out at node number 1 v1 theta 1 is equals to 0 due to fixed. At node number 2 and 3 is fixed with the roller support along y direction. v2 v3 is equals to 0. Then theta 2 and theta 3 should be fine. Eliminating corresponding rows and columns with respect to v1 theta 1 v2 v3 is equals to 0. With respect to v1, first row first column has been eliminated. With respect to theta 1, second row second column has been eliminated. With respect to v2, third row third column has been eliminated. With respect to v3, fourth row fourth column has been eliminated. Third row third column is remain same. Sixth row sixth column is remain same with respect to theta 2 and theta 3. Now 6 cross 6 matrix is reduces to 2 cross 2 matrix after applying the boundary condition. Just we have copied these values here, 32, 64 and 12.5 I have taken common. 10 to the power of 3, 10 to the power of 3 cancelled. Theta 2 and theta 3, minus 16 and 32. We know that convert this matrix in terms of algebraic equation. Write down the equation, calculate the value of the theta 2 and theta 3. This is one of the method. In your external examination, to make easy for this one, use the calculator directly. No need to convert that algebraic equation to reduce the time. Just represent that equation A in equation B. Then substitute the value of A1 into this B1 into this and C1, two unknowns. Equation you take down, and then 32 into 12.5, 64 into 12.5, this is a A1, this is a A2, B2, C2, A1, B1, C1, A2, B2, C2. Click equals button, you will get a value of x that is equals to theta 2, value of y that is equals to theta 3. After getting that all the values, we know that represent the nodal displacement vector. We are not interested to find this nodal displacement vector. We need to find out a displacement maximum deflection at the midpoint. He has a given at the midspan in a given problem. To find out that, these are the unknowns is required. So what are those? Deflection at a midspan. Deflection at the midspan of the given element. We have derived this equation, right? I have told in a formula list to remember this equation. Directly we can use, or else we'll drive. Both methods are correct in your external examination. If you will skip that derivation, it is well and good to reduce the writing time for this particular problem. Directly you remember that equation, that is a better one. So again I have derived for your conveniency. We know that a Hermite shape function in the field variable displacement relation V is equals to H into Q. We have found the value of H1, H2, H3 and H4 that I have substituted here, where we need to find out the displacement at mid of the span. Zeta is equals to 0. We are not considering zeta is equals to -1. Zeta is equals to +1. Zeta is equals to -1 left hand side, and right hand side zeta is equals to +1. We need to find out the maximum displacement at midpoint. Zeta is equals to 0, right? So when we'll take that zeta is equals to 0, this Hermite shape function is yields to field variable V maximum displacement at midpoint. V max is equals to 0.125 LE, 0.5 minus 0.125 LE into Q. When we'll consider an element number 1, E is equals to 1, this becomes L1, and Q becomes V1 theta 1, V2 theta 2. For example, if I'll consider E is equals to 2, this LE becomes L2, and this displacement vector becomes V2 theta 2, V3 theta 3 for element number 2. For element number 1, V1 theta 1, V2 theta 2. That is very much important. Carefully you take down. So now I'll take this as a element number 1. We have LE becomes L1 is equals to 4 meter, V1 theta 1, V2 is equals to 0, theta 2 is equals to minus 0.02285. Then substitute that V max, this equation becomes 0.125 into 4, 0.5 minus 0.125 into 4. Then you have this V1 theta 1, V2 theta 2. V1 is equals to 0, V2 theta 1 is equals to 0, V2 is equals to 0. This we have found substituted value, right? Now we have 1 cross 4 matrix is multiplied by a 4 cross 1 matrix. Will have a 1 cross 1 matrix, right? So when we'll multiply a row with respect to the column, we have 0.5 into 0, that is 0. This value into 0 plus of 0. This value we have again here 0. Then last value we have minus 0.125 into 4 into this value minus 0.02255. When you will calculate this value, that value which is equals to 0.011425 meters, the maximum displacement is occur at element number 1 is this one, and then I will convert this value in terms of a millimeter. 11.425 millimeter displacement is occurs at element number 1 at the mid. The maximum displacement occurs in a element number 1 for a given beam element, which is equals to this value. This is a maximum displacement at element number 1. Now we need to find out this one, second bit. Now I will take as element number 2 to find out a maximum displacement which is occurs in a element number 2 at a midpoint. Directly I will take that equation we have derived. E is equals to 2, then LE is equals to L2 is equals to 4 meter, V2 is equals to 0, V3 is equals to 0, theta 2 and theta 3 we have found. We have this equation, substitute all those values, so calculate this. After simplifying this matrix, we'll have that maximum displacement which is occurs in element number 2 at midpoint minus 0.03735 meters in element number 2. Vmax is equals to minus 37.135 millimeter in element number 2 will occurs. Maximum displacement which occurs in element number 2 at mid span, the given beam element for a load of 24 kilonewton per meter minus 37.135 millimeter, right? And then next bit what he has asked to find out a reaction force. As usually we know that the equation of a reaction force so many times we have utilized in a solutions of bars and solution of trusses. Same equation we'll use. R is equals to KQ minus of F. R is in a reaction support and K is a stiffness matrix, Q is a displacement vector, F is a force vector. We have found that force vector, displacement vector and stiffness matrix individually will found. In the previous method we have adopted a complete matrices. We have taken, if we have n numbers of element, global stiffness matrix we have used to find out the reaction force in a bar element and in a truss element. But here will not use a global equations in a beam element to find out the reaction at the support. We'll use a individually to find out the reaction at the each support which is occurring due to the application of a load in a beam element. Why the variation of the load will take place in a beam element, but in a bar element we'll assume that there is a displacement is uniform, load is uniform. That means the combination of more than one bar is set as a truss, that is also a bar element. In the both condition we have taken a global stiffness matrix, but here we will not take a global stiffness matrix, global force vector. All the globalized equations will not use in a beam element to find out the support reaction. In the beam element separately will take with respect to the element. Now I'll consider in element number 1 the reaction force. We have R1, R2, R3, R4 for element number 1. Node number 1 we have reaction R1, R2 with respect to the transverse displacement and with respect to the rotation. R3 and R4 with respect to the transverse displacement at node number 2 and the rotation at node number 2. We have the stiffness matrix substituted. We have the displacement vector V1 theta 1, V2 theta 2. We have here F1, F2 and F3, F4. All the values we have found. We are not taking this directly global displacement vector here. Global force vector we are not taking, we are taking a elemental force vector. This is the element number 1 force vector, element number 1 displacement vector, element number 2 displacement vector. We'll take here to find out the reaction at each element. So this one V1 theta 1, V2 theta 2 is a F1, F2, F3 and F4. We'll substitute this value, we'll multiply and then we'll subtract this value. We'll get this answer. Directly I have given a clear idea in a bars problem as well as in a trusses problem. You go through on that in a bars problem, reaction support, how we are finding, and in a trusses problem directly we get it. After resolving these matrices, we'll have these values at reaction will occurs at node number 1. These are the values, and at node number 2 these are the values. In terms of a kilonewton we have converted this 10 to the power of 3 in terms of a kilonewton. That's all. Similarly substitute in element number 2 all the values. You'll have found the values. This is the V2 theta 2, V3 theta 3. These are carefully you take down. The force are there F3, F4, F5 and F6. This one F3, F4, F5 and F6 for element number 2. This is element number 1, element number 2 from here to here. So we have this, substitute those values, we will get this reaction force, convert in terms of a kilonewton. Thank you for listening my lecture. I have given a clear idea how to find out the global displacement vector for a beam element. After that, how to find out the maximum displacement occurs at the midspan of the beam. In next video, we'll get the idea for a point load. Now we got the idea for a distributed load as per your VTU syllabus. In next video, we'll learn on a point load and a moment. Thank you for listening my lecture.